On any given day, more than 100 naval vessels and 70,000 sailors and Marines sail the world's oceans defending freedom and protecting America's interests. With global presence comes the need for global logistics that must overcome the tyranny of distance, complexity, opportunity cost, and safety. For decades, naval forces have relied upon side-by-side steaming for fleet refueling and sustainment, an operational maneuver called underway replenishment, or UNREP. The catch-22, while capital warfighting assets need fuel, stores, and ammunition for combat readiness, UNREP requires that they be pulled away from combat duty to obtain that readiness. Can we do better? Can sustainment be done over long distances with more tonnage per sortie? UNREP is often complemented by Vertrep, the use of fleet helicopters making shuttle runs between two flight decks only yards away from each other. Vertrep helicopters, with their half-century-old gas turbine open-rotor powertrain designs, are mere augments to current UNREP operations, a role that detracts from their core lethality missions such as mine warfare, surface surveillance, and drone intercept. So the issue stands. To replenish major naval assets, combat operations must be halted, vital resources must be retasked. The limited number of naval assets needed for global presence and response demands a better sustainment architecture. Can enhanced Vertrep be part of the answer? Can a single shipping container with 40 tons of supplies be carried over 1,000 miles of ocean in less than 8 hours? KRyanCreative has partnered with the University of South Carolina to develop scalable electric propulsion technology for vertical lift that will provide ultra-heavy payload capacity in the footprint of a medium-lift airframe. This collaborative team seeks to transform UNREP architecture with a specific focus on limiting side-by-side steaming while on station and using ultra-heavy vertical lift as the primary tool for sea-based logistics. This proposed program, called Vertrep at Scale, accelerates naval vertical flight into the electric era for mission agility and warfighting efficiency. The naval next-generation ultra-heavy vertical lift aircraft will rely on advanced drive technology embodied in a levitated advanced rotor system, or LARS. LARS is a fully superconductive direct rim drive motor coupled to a hubless, high-solidity rotor system. LARS greater than 90% efficiency produces thrust in a distributed propulsor arrangement that makes carrying a 40-ton shipping container possible. A distributed electric aircraft using LARS can lift higher payloads in the same footprint as the V-22. A LARS-based propulsion system in an ultra-heavy vertical lift airframe can make Vertrep supplant UNREP as the primary mode of naval at-sea sustainment. LARS research tackles the challenge of torque density, which is the single most pressing problem in vertical lift today, and one factor that inhibits industry from scaled innovation. Torque density solutions start with a magnetic bearing that enables high-solidity rotor blades to capture greater span-wise lift, coupled with an optimized air mass flow through the center. Preliminary research is closing the gap between hover power available from advanced power generation and energy storage technology and power required for freight container payload capacity in a distributed electric propulsion vehicle. Our next research phase will improve on rotational friction, stress concentration, and structural weight, challenges that inhibit investment in scaled rim drive solutions. Captain Ken Ryan, U.S. Navy retired from KRyanCreative, is the principal investigator and principal aircraft designer for the novel air vehicle that guides LARS development. His experience as a fleet operator, test pilot, systems engineer, and requirements officer informs his approach to tackling hard problems, be they technical or operational. The University of South Carolina is the partner research institution led by co-principal investigator Dr. Abdel Bayoumi, the chair of the Mechanical Engineering Department. Dr. Bayoumi directs the Center for Predictive Maintenance, housed in the McNair Center on campus, where expertise in material behavior, tribology, health monitoring, and digital transformation resides. The University of South Carolina is a celebrated academic and industry leader known for creating AI-based digital models for physical systems, digital twins, and mechatronic advancement. Prior efforts for the armed forces have explored the advantages of integrating digital models for predictive health usage monitoring in legacy helicopter powertrains. Our research will find the inflection point at which a rim drive design can scale and meet the technical challenge of high torque density for envelope expansion. The Vertrep Scale project integrates high-temperature superconductive technology within a scalable distributed electric propulsion system. LAR's research will de-risk impediments to attaining near frictionless blade assembly rotation and find the design point for peak aeronautic efficiencies. LAR's Phase 1 will lay the predicate for ground technology demonstration that will validate the concept, design, and manufacture of a magnetic bearing that integrates advanced superconductive materials. With stable torque delivery in a frictionless environment, rim drive scaling can proceed to a prototype from which airframe design options will be illuminated. Exploiting superconductivity is the best technological approach to scaling eVTOL into heavy and ultra-heavy markets that will transform the industrial base and have a consequential impact on naval operations, national security, and global logistics writ large. With Vertrep Scale, the Navy can project power with unmatched logistic agility.